Hello team! Welcome to the video guide for programming assignment 5t, the interpreter test-driven development. The last time we did test-driven development, we looked at programs as data, went inside the cool reference interpreter, and automatically generated some bad cool programs. Those techniques are both still good for programming assignment 5t, but they're a bit harder. It's just more expensive to generate well-typed programs that go wrong. So this time we're going to focus on how to generate good test cases from first principles by looking at difficult parts of the cool operational semantics, that is, the rules for how we evaluate cool programs. And together we're going to take a look at aliasing and dynamic dispatch relatively briefly. We'll do a live submission demo, and then I will leave you with some hints for places in the specification to look to guide your test case creation. All right. So to get started, I've just downloaded the cool examples zip file from the web page, and let's see how far we get in programming assignment 5t interpreter testing if we just resubmit the given cool examples. So it's worth noting that there's a size limit in programming assignment 5t in addition to the number of test cases that you can submit. So some of these things like arith are just too big. But we ended up with hello world, hello int, Harry Scary, new complex, and print cool. And these cool examples are already revealing some defects in previous student interpreters. We're discovering 6 of these held out defects. All right, well, let's see if we can write a cool program together to flesh out a few more. I'm going to write one called aliasing, test case to show off aliasing. Recall, aliasing is when two names refer to the same object in memory. So I'm going to make, in order to show this off, I'm going to need objects, and sometimes aliasing doesn't show up as well with primitive objects, so I'm going to wrap them. I'm going to have an int wrapper class that will have an integer field, and we'll have a way to set this field with a new int, and we'll see what we want to return later, but my int will get this new int, so I guess we're returning an integer. We'll have a way of getting the current value, where we just return my int, and just for fun, I'll even add an increment option, right, that will add 1 to whatever's going on. So my int gets my int plus 1. So there's my class int wrapper, and now I will have my class main that inherits from IO because I want to print things out. And what I'm going to do is make a bunch of these int wrappers and try to automatically create aliasing. Try to have 2 names that refer to the same object in memory. And there are 2 different ways we can make up new names. Ways to make new names for the same object. One is formal parameters plus dispatch, and another is let. And maybe we will try out both. So we could have main, which returns object, and we'll probably want to do a lot of things in main. So we'll immediately start with a block. And in order to tell the difference between these objects, I'm going to set them all to different things. Let's set A to 11, we'll set B to 33, and C to 55. And these numbers don't matter except that they're all different, and they're all far enough apart that when I call increment, we're not going to be confused. And let's say I make a new method that's going to operate on these int wrapper objects in order to reveal aliasing. Right, maybe there's some sort of X, which is an int wrapper. In order to show aliasing, oh my God, how did you let me live for that long with this crushing English mistake when 2 names refer to the same object? So I'm going to need 2 different variables. And to reveal aliasing, well, I might try to print out what's going on in X and also try to print out what's going on in Y. And then if I increment X, I can once again print what's going on in X and what's going on in Y. All right. And let's see what happens when we process A and B. We expect to print out 11 and 33, and then 12 and 33. Let's see if this program runs correctly. Probably we've made some typos. No. Here's 11 and 33, and then 12 and 33. And we can make this just a little more visible by putting in some spaces. We don't need those. 11 and 33 and 12 and 33. But here's the trick with aliasing. What if we pass in C both times? So now both X and Y refer to C. So when we print them out, we expect the same value, 55, 55. But when we increment X, that's ultimately changing the myint field of one object. So then when we read from X and Y later, both of them will be incremented. Let's just go see how that goes. Here, 11 and 33, but we only incremented one number, 12 and 33. But in the second version, we've got 55, 55 goes to 56 and 56. That's the aliasing. A change to X also changed Y because X and Y are aliases for the same memory location. They point to the same memory location. Now, we did mention that there was another way to show off aliasing. We could potentially have local variables. Make variables like these, P, Q, and R, some of which refer to the same thing and some of which don't. And now that I'm in here, I can try to do some of these same sort of actions. We'll print out P and Q and R, and then maybe we will increment P. And once, oh my gosh, and once again we will print out P and Q and R. Let's see if this program works correctly. Parse error near cool hates me. Ah, yep. All right. So now we've got 33, 33, and 56, which becomes 34, 34, and 56. This is the aliasing. Again, we had one increment, but it changed this variable. Why is this still 56? Oh, because we incremented it the previous time. All right, so we've tried out two ways to see aliasing, and let's just add our new handcrafted alias test case, and we'll try to resubmit it. So previously we revealed 6 of these defects. Let's see if we can find any more. 1, 2, 3, 4, 5, 6, 7. Ah, we did find one more. Which one was it? Ah, it looks like it was the last one, 122. All right, so by thinking very hard about this sort of aliasing, it turns out that that was one of the defects that we were interested in. Now we saw along the way, let's call this, we saw along the way that one of the ways to create aliasing was to call a function. All right. Let's remove a lot of this let maneuver. And now I'm interested in making a test case that shows off what happens when we call functions and how we push arguments, and also some of the other interesting tricky bits of the type system. Right, we want to think about things that are difficult for typing or interpreting and see if we can make test cases for them. There was an entire lecture felt like on self-type, maybe we should try that at some point. So for example, I could have my increment method return the self object. And now, maybe I would want to try out subclassing int wrapper later. I'll do it right now. Int wrapper child inherits int wrapper. This should work. I should be able to put the child type into the parent type. When I'm processing, perhaps I expect the parent type. But now that I have these three variables a, b, and c in this process method, rather than just passing in a or b, I could also have side effects in my order of evaluation. Right? Each of these increments, this is sort of like calling foo of x++ and y++, and that's not exactly the same as foo of ++x and ++y, if this were language more like C. So part of our test can be to sort of check and make sure that we're doing all of this correctly. Are we handling self-type? Are we handling side effects in dynamic dispatch? So just rename this a little bit better. This is dispatch, self-type, side effect. Right. So now we can add something like this to our test suite. Previously we'd been getting 7 of these. We'll just make sure it has the most up-to-date version and resubmit. 1, 2, 3, 4, 5, 6, 7, 8. Oh, we've gone up one more, and it looks like one of these issues, either self-type or side effect, was one of the other held out interpreter defects. And to figure out which one it was, we could split that test case in half. You could make one part that just did the self-type and one part that just did the side effects in order to make the names of your test cases more evocative and have them be smaller so that later when you run into defects, you don't have to dig through them. All right. Those are the only two I'm going to go through directly. We're almost there. We're halfway through the required number of defects we need to reveal. But I did want to bring to your attention certain hints or places to look. One of these, let's see if we can pull up the cool reference manual. Do I already have it? All right. Way at the bottom of the page on the operational rules, there's a list of all of the possible cool runtime errors. Now, some of them, like heap overflow, we don't have to implement. But for the other 6, you should probably try to make test cases for each one. Show off dispatch on void, case on void, show off missing branch, show off non-missing branch, show off division by 0, show off division by non-zero. I recommend considering each one of these runtime errors because those are important for the interpreter. Similarly, I strongly recommend that you look at all of the internal functions. So for the base classes like object, we've got these internal functions like abort and type name and copy. You should probably try to write some test cases to make sure that all of those are working correctly. And in particular, things like in-string and in-int have a lot of conditional behavior. If an error occurs, it returns the string of length 0, blah, 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 string reading in null. Recall that for this assignment, you can submit your own handcrafted input files. So you might write some tests for inint where you pass in negative numbers, positive numbers, garbage, spaces before numbers, hexadecimal numbers. Try it all out. Similarly, I strongly encourage you to try out both static and dynamic dispatch. As you're going through the operational rules, all other things being equal, the bigger a rule is, the easier it is for a student to get just one thing wrong and for that to be some sort of error that you'd have to reveal. So since dispatch and static dispatch are so huge, those are great places to look. And static dispatch is also just complicated. Similarly, case. The case expression in cool is a lot like the match expression in OCaml, but just draw your attention to this, right? Closest ancestor. This part essentially requires your interpreter to implement the least upper bound or some sort of nearest ancestor calculation. So since this isn't defined as mathematically as the rest of it, this is a fruitful place for errors, right? So I just double check. There's a lot of processing in case about the order in which things are considered, right? Requires the class hierarchy to be available at runtime. So I would encourage you to pay careful attention to it. All right. That's it for this video walkthrough. There's really no shortcut this time. I encourage you to think about everything that could go right or that could go wrong in cool and try to create a number of powerful defect revealing test cases. Good luck.